This video is the complete course on the optimized pit design workflow presented by Grant Wenker at the 2022 Carlson Software User Conference. For more information on the annual user conference, be sure to check out info.carlsonsw.com/user conference.
There's a grade copper equivalent. And you can see I've got anything less than copper equivalent of 0.1 is waste, and then just 0.1 to 1 all the way up to 5, CU, EQ. So those will be the grades we're looking at. And then we'll view that with block model. Go down to block model 3D viewer. There's the block model. CU, EQ. And then you also need to pick which grades you're going to process on the model. Let's just leave everything turned on and checked for viewing. We could limit it with the top and bottom, or maybe a bench that you're looking at, or an inclusion boundary. But we'll just put them all on the screen and see what happens. And again, it looks like a lot of waste coloring here. So that's the gray blocks. So let's go ahead and just freeze those. I'll go to the block model tab, come down to the waste and double click on it and freeze it. So all of the waste around there is now gone. And you can see then almost a vertical seam or vein of this CUEQ ore. All the gray around it was waste that's now been taken away. So this will be the ore that we're going to find some pitch shells on based on different parameters and equations that we enter in. There's not a lot of the high grade, which is the red material and yellow, but there is a pretty good amount of it right in here. And it's just sort of scattered in other places too. But the blue and the purple is the lower quality, and that does show up deeper. So that kind of gives you an idea, of where the good stuff is and where we're going to design. Where this will give us an idea where we're going to go, how deep. Okay, so it's really just two commands. There's a lot to them, obviously, but under the block model pull down, it's at the very bottom. You see two commands. There's a prepared value block model, which is just like it sounds. And then there's the actual command to run it, which is the optimized pit design. We are using a maximum flow, max flow algorithm. You might have heard of Whittle or Lurch-Grossman, which we used to use Lurch-Grossman, but we switched to this one. It's faster, it has similar results. And it just allows for some nice custom equations that you enter in to generate the optimum pit shell. And it'll create a tin file when you're all done. And the tin file will then go down and you can contour it or take that and do more detailed designs, with benches and ramps and all of that. But this will just be an overall generalized pit tin shell of the depth that you can get to. So we're going to start then by running this prepare value block model. So that's why I wanted to show you initially the geologic block model. That's what you start with, and then it will convert that to a value block model. So let's go to prepare value block model. Now there's two ways to go, right? As soon as you run the command, you're at a decision. Are you going to go with a block model or a stratified geologic model, which we'll do later. So this first time we do it, we're choosing the CUEQ BLK. Notice it looks for pre-calculated, with the PRE extension is referring to a pre-calculated geologic grid-based model. That'll be the stratified one later. Or you could do a already processed. The BMV is a value block model that's already been built. Maybe you were in here before, you just want to bring it up and make some changes. And the others are just ASCII text. So in this case, we're going with the CUEQ block model, which is what we just viewed in 3D. You saw the grades of copper. The left side are fixed attributes that automatically will appear, such as the volume of each block, the rock or the strata, the position in the strata, how, if it's a geologic strata, geologic model, how high in the strata is it? And then any attributes from the block model. We've got the CU, EQ, and the density. And then the Z centroid, that's the Z elevation of each block centroid. So when we are going to maybe calculate the haul distance or the height, the lead and the lift of each block, the height you need to raise it can be calculated and affect your pit shell. The economic value inputs, you can have just a straight attribute. So if you have in your block model blocks that contain a dollar amount, then you can just click that attribute and go right into the optimized pit design. You don't need to do any equations or anything else because that's been done to calculate your value block model. We don't have that. We just have pure geologic information. So we're going to switch that over to equation. Another thing to do, since it is a block model, it's flat, mostly flat at the top. You did see a little bit of things changing there, but I want to cut that model by the topo. There's no need to analyze blocks that are above the ground surface. So this is something we should always do every time you come in here. If you're using a block model, choose the cut model by topo, and then go find, at the very bottom, is the topo.grid, and it's 5 by 5 in the cell size. And then we'll do cut above surface. Obviously, you could choose a lower constraining surface and remove all blocks below there. But we're just going with the topo, and it actually didn't do a whole lot. It removed 117 blocks that were above the ground. So those are out of the picture. We're not going to have to move them to do the economic analysis. And you can see right down here, there's 605-ish blocks. Volume, this is metric again, 75 million cubic meters. And before we get into our equation writing, I'll just point out you can export this to a GSLib block model, just pure ASCII text model. So this, again, is making an economic block model. And you can then export that out to these other formats. But in our case, we're going to go right now into the equation, and we'll select valid equation. And this will be then our equation writer. We've got 3 tabs across the top, and so now we'll spend some time in here writing equations to calculate our value block model. Just discussing in text all the things we just mentioned. For example, here's your attribute. We're not using an attribute from the model. We're going into define equations. We cut the model by the topo. Here's 3 output or export options when you're all done, which we haven't done it yet. And then we do have a summary. Notice right now our total value is blank. We have the total blocks, the volume, but this economic value is blank because we haven't done anything yet. But this is not what you're actually mining. This is going to be the economic value of the entire block model. So if you were to mine every single block that it showed there in the viewer, that's the value. You'll never do that, but at least you'll see some numbers there. When we run it, we're going to get smaller, much smaller numbers. All right, so then back to the define equations. We have some out there. I don't want to start from scratch, so I'm going to bring them up and load them up, and then we'll just talk through each. We've got 5 listed here, 5 or 6. We'll talk through all the calculations that were defined. Come down and hit load. Oh, sorry, before I do, I'll mention over here, the purple. Those are the attributes from the previous screen. See over here on the left, attributes already brought in, they're fixed. You can't change them, they exist. They will be used as variables in equations. You'll see some other colors appear over here later on when we start building these equations. So now we'll come down here and hit load. And I've got about 5 or 6, 7 of them already calculated. So let's start small here. I'm just going to go define equations with the 20. All right, so that brought in some saved equations for me. And this is obviously when you come in here the first time, this will be you'll be starting from scratch, and so you would just come in and add a new equation. And it's just like any Excel type or the grid file utilities. You can just punch them in here. You do need to, I guess, get into the mode of doing some equation writing, like any mine engineer needs to when you do this optimized pit. There's no really go button here. It does involve a little bit of imagination, thought on how you want to calculate these, and even just writing clean equations. Make sure your parentheses are in the right spot, etc. So let's talk through these now. All right, so I first am calculating tons of material. And that equation I just entered in as the volume, which is down here, already a predefined attribute. It's the volume times the density divided by 1,000. So that just gives me metric tons again. That's 1,000 kilograms per ton. Pretty simple. So then we take the mining cost. So this would be the cost for removing the blocks. And that would be calculated as the tons times the mining dollars, which over here I entered in constants. So before I look at that, let's just add another constant to show you how that works. Add a constant. The name here will be, I don't know, let's say, do I have anything for, I don't. Let's say a haul cost. We're not going to use it, but I'll just show you. Enter in a new attribute called haul cost, and that might be, say, I don't know, $1 per kilometer or something. So there it is. It put that new predefined variable. It's a fixed constant on my list, which is the green. Those are the green variables in here. And then you can then refer to that over here, which is what I'm doing with mining dollars. So I've got tons, so it's 5 times the tons. And then in this example, we just are taking an arbitrary elevation of 195, which is about the average elevation, maybe that you have to haul it up to, or maybe that's where the top of the potential ramp will be, is 195 minus the Z centroid, which is the elevation of the centroid of each block. So if you're down at the bottom, I believe it goes negative below sea level, you're going to be lifting this up, maybe 300 meters. So that's the height that each block is being moved times the lift cost here, which is in this case another 5. So that's the mining cost as an example. You can use any variables you've defined and any of the predefined attributes to calculate a mining cost. That's just mining the material. Then we're also going to then calculate a processing cost, which will be the same tonnage, which is calculated here, times another constant, the processing dollars, which looks like 9.9 processing cost, times is ore. What that's referring to is if it's only the copper ore blocks. You don't want to process all those other gray waste blocks because we are going to have to move a lot of those to get to the ore, but you don't want to pay for processing those. And so that is ore is just an attribute name I made up, but it's also here a conditional variable. It's blue. There's 2 of them. And just take a little detour now. We'll come back to these equations and talk through them again, but let's now look at where these 2 blue conditional variables came from. We'll click on conditions. We have an expression here. The CU-EQ is greater than 1. And this is why I showed you that block model earlier. Anything greater than 1 was ore, I believe, and then anything less than 1 was the waste, or the gray blocks that we saw in that equation, in the viewer. And then you can do a true and false. So you double click, or just single click actually, inside the true false cell. And then this is where you decide if the block is going to be an OR block or a waste block. So if the CU-EQ is greater than 1, if it is true, is OR, the variable I made up, is set to 1. And the waste is a 0. So if you can imagine that on the previous equation then, it's only going to use the processing cost on the OR blocks because the rest will just be multiplied as 0. If the CU-EQ is less than 1, less than or equal to 1, I believe, then the OR is going to be 0 and the waste will be 1. We're not actually doing anything on waste processing, but we will have to, of course, haul the blocks of waste, but we're not going to do any additional costs on those. And then, okay, so I'll hit exit on that. Not going to change that. So that's just that's how you decide if it's OR or waste. Exit there. And then there is another kind of a fancier option on how you want to evaluate these conditions. So I want to test condition 1. It has to be calculated before the result, the revenue, the processing, and total cost equations. I don't have to calculate this before the tons and the mining cost equation. Let me move this down. I'm referring to these. So I don't care. This is or variable has to be calculated before these last 4 items. It doesn't have to be calculated before the first 2. That's all that last cell is referring to. And you can just move these back and forth, like so. And that's it. All right, so review then. That's where the 2 light blue came from. And then condition 1 here is the dark blue cell, and that's just showing you that there are some conditions used to calculate is or is waste. Back to the document. And now we're going to continue talking through the additional equations. So we got to the is or. So that'll be the ton of each block times the dollars to process the ore times 1 or 0. If it's a 1, you're going to get some cost. If it's a 0, there's no cost to process it. That's all it is. The next equation we're creating will be a total cost, which would be just basically mining cost plus the processing cost. So just the cost to mine plus this gives us a total cost. That's the total cost of removing all those blocks of ore. All right, so now we're switching over to some revenue calculations. I made a new variable. I just called it revenue. You can just arbitrarily type in some attribute names for your equations. And I'm calculating that by the tons times the is/or, which is going to be a 1 or 0, times the actual grade of the copper. If you recall, I had 1, 2, 3, 4, 5, I believe was the max. Times, I just have another fixed constant here. I put in a market price, in this case, of $20, possibly. $20. And that's a market price. So that market price can change. And that's why I had about 6 or 7 different equation files, because that's the one field I was changing based on whatever it's selling for that day. You can see how the pit shell will change. All right, so that calculated a revenue selling. That's the amount you would make for selling each block. All right, then the result, that one's fixed. You can't change the result. You see that's here as an equation, but it's always going to be there. And that's simply row 5 minus row 4. That's the revenue minus the total cost. And hopefully there's some left over there and we can be profitable. And then we'll do a save and a save as. So let's talk through this. We've got the attribute list on the right. We just did the equations tab. We looked at the conditions tab, is or and is waste. Something light flickering. So it just mentions again if the copper is greater than 1, then condition 2. Otherwise, it's going to be waste if it's less than 1, and or is a 1. Then we looked at those two windows. You got this one, then plus the condition to be calculated before or after which other attributes. All right, so now we can test the math. We have another tab. It's called the Test tab. You'll see it here. It's the third one. And it brings up the variables here that can be entered in. So picture just say one block, for example. In this case, maybe a block is 1,000 cubic meters. And it might have a nice high CUEQ of 5. And its centroid, it might be down there at 100 elevation. These are just 3 numbers I entered in to test out my math equation. We're not using the strata predefined attribute. We're not using position in strata. And then the result is something that I just hand calculated off on the side on a piece of paper. So let's go and look at those tests. So using the following tests, I just said, okay, this block, I don't know if it is 1,000 or not, but I just put it in as a, maybe that'd be 10 by 10 by 10, 1,000 cubic meters. It has a copper of 5, and it's at 100 elevation. So punching those values into, let's go over here, to the equations gives us 1,000 times the density divided by 1,000, which is only 2,600, the same. Then we take it down to the next level. It'd be the 2,600 tons, darn it, 2,600 tons times 5. The mining cost, which is over here in green, 5. Did I spell that wrong? Mining dollars. Okay, mining dollars, there it is, 5. And then you've got the 195 minus the 100 elevation times the lift cost, which is 5. So that manually calculates here on my calculator to 13,475. Then you enter in the processing cost, which is the 2,600 tons times the 0.9 right there, variable in green, times 1 if it's OR. If it's obviously got a CUEQ of 5, it is OR, so that's going to be a 1. All right, moving along. Then we bring down the last, the mining cost plus the processing cost gives us a total of 15,815. And then the result, if this is all working right, should be 84. Oh, sorry, that's the revenue. It's 845,000 minus the mining cost is 829. So if that's, let's see, I'm not sure what market price one I have this at. So let's try it. The result here is something you type in. But again, I had 5 equations there, so let's see if this is the one. It'd be 829,185. I actually think it's the wrong one. 829,185. And then you hit run test. And it should be red or green. So that's showing a test result of 244,185 is what the test should come to. And this one is the green, but this one is showing a market price of $65. Okay, so we can change that. I just ran the test with the market price of $20. So if I change that to $65, that's the only thing I'm going to change. Rerun my test. Voila, it's green. So now my equations match up with my values entered in. And that's all it is. There's no result given there. It's just for you to make sure that your conditions and equations are all set up properly, and then it's kind of a way to check your math. I'm not going to save this one because I just changed that market price. I do have other ones out there, so again, I'm just going to hit load to show you them. I ran this same pit shell with 20, 22, up to 35, 50, and 65 as the market price. So quite a big range. And so I guess we'll go ahead and do one. We'll run this It doesn't take long at all. So I'll switch this back to a 20. Or I suppose we could do a new one that really doesn't exist. Let's say it's 32. Market price 32. I'll save as, do a save as, and I'll just go and there's a 35. I'll change it to save it as a market price 32 equation. Now don't worry about the test. That's, again, just a reference for you. Obviously, the test would fail, again, unless we were to recalculate the result. But everything else is good. And so I can just hit OK to get back to the previous screen. So this is kind of your main window. And this is where we started. It's actually calculating right now. And it just finished. So if you were to mine every single block inside this rectangle, that's the block model extents. Now my economic value just updated. I'm at a negative 1 billion with a B, 300,000, because you saw all those gray waste blocks. And there's no way you're going to mine all this. We just want the ore blocks. But if you did mine the entire model, that's how much you'd lose. I believe that's the first setup. We're ready to now take that. It saves it as going to make a new block model value file. So we haven't done it yet, but as soon as you exit this and hit OK, it'll ask us to create this file. Hit OK, and there it is. It says select block model, BMV. Now this is a little different file format than the BLKs we were looking at, geologic files. This, again, is just a binary. You can't really view it or see it. Value block model. So I'll just call it market price 32. All right, so it just wrote it out. It wrote out copper top, copper bottom, and then all the in between there, each block has a value associated with it based on if it's waste and what the copper Cu, EQ is. And that's really half of the optimized pit design routine is you first prepare this value block model, and then we go and run it. So let's go and check that in the document. We go to optimize pit design, and we'll load the file. There should just be the one file that we just made. So now we go back to block model, and we choose optimize pit design. And there's the one file. I guess it's not as big as I thought. It's 84 meg on this one. Maybe the other project is 200 meg. It did take longer. So I'll load up the 84 meg value model. My blocks, again, it's metric. They're 5 by 5 meters. And you can control or set your side slopes on different azimuths. So an example would be 0 is straight up, 90 is to your right. 0 to, say, maybe 180 degrees would be north to straight south. Maybe you want 65 degrees. I'm not going to do a variable one, but an option there would be, then you would round it off. You'd say, okay, from 180 to 360, I maybe will allow a different slope. Maybe the material is less stable on the west side, so I might go with a 45-degree slope. That's how you would enter it in. But I'm just going to have one. I'll do 0 to 360. That's 65 degrees on the angles. I think that's what I used. We'll double check. I'm pretty sure it is. And then there's one little option to pull down here on wall angle check neighborhood, and the default there is 2. And what that's referring to is how many blocks it will look at in the direction that it's cutting to get to your angle. So if you had just one block in there, for example, if I had this set to 1 and I wanted to do a side slope that's really flat at 20 degrees, I really probably couldn't do that because one block is going to be going up at nearly at least 45 degrees or 65 degrees. So if you have a problem or you get an error message, you might need to just increase the number of blocks that it analyzes and removes to get to that angle of your high wall side slopes. So 2 works pretty well here. So it does two things again. You set how many blocks to look for the angle, and then you're defining the angles on all directions, north, south, east, west, just by an azimuth. And that's it. Hit OK there. And that's running. Now it's in the background, calculating. It says in the bottom there, building max flow graph, running max flow optimization. And it runs through it a few times, and I don't recall exactly, but I think it's maybe 1 or 2 minutes on this model. Let's see, we've got a tin file. So it's done. It's saved out, a tin. And you can see I do have other tins based on those other market prices I entered in. So we'll do the same. We'll call it revenue of 32, which is the new market price we're doing today. Save it. And you can see at the command line there's some information there we'll get to in a second. It does now save this out as a BMV, a value block model. I usually just give it a new name. We'll just call it 32 output. And it's done. So it's completed. Let's take a look at the results down there. Finished with a total monetary value of $46 million, a total volume of 3.4 million cubic meters, and I got 27,000 total blocks to do that. Let's see what this other previous one did. There's your total size, how many blocks it's removed. This run was $155 million, a volume of 5.8 million units, cubic meters, and 47,000 blocks. So I'm not sure which one that was, but it was probably around the lower end of the spectrum, like the 20 market price. All right, so now we've got all these surfaces out there, and if you're in the drawing, you can see these cross sections to the right. Let's first just look at that file that we made. So I'm going to go to View. What's the best way here? I'll probably view the block model first, and then I bring the surface in. That way you can compare the surface with the model itself. So let's do that. We'll go to Block Model, 3D Viewer, choose the model and the grades. I'm going to turn off the waste. You saw before that was the big, massive gray ore body of the waste. So we're going to turn that off so we don't have to freeze it. And we're looking at just the copper ore. And then we'll go to the Model tab, hit the little triangle pyramid in the top to add the surface. The one we just made today was optimum pit revenue of 32. So you can see the shape of the blocks inside. I don't think I'm exaggerated. No, this is not exaggerated vertically. That's a 1-to-1 scale. So that is a 65-degree slope going up the side, and we'll verify that later. I'll show it to you. But based on the parameters we put in today with the 32 market price, that's the limit right there. You can see there's a lot more to go down below. But we concentrated mostly in here where the yellow and the red colored blocks were. Down here there's poor, lesser quality, so we kind of ignored that, didn't go and concentrate there. Okay, I'll exit. And let's just do that same thing on the $65 market price, just to show what the depths will be there. I'll go back to View. I guess I could have stayed in there and just added a surface, my mistake. And then I'll go to the model, add the 65 revenue. And you can see the difference there as we go a lot deeper. It's a lot bigger, wider pit shell. And then let's bring in the 20 revenue surface, which is the smallest one I have there. Revenue of only $20. So you can't do much there. It just concentrates it up here where it's really shallow, close to the surface, and that's as much as you can get. Let's go ahead and turn off the red one. You have to go and hide it. All right, so here's the 20. You can see it's a very tiny, minuscule pit shell. That's as good as we can do when the market price is that low. In fact, we don't even get down to the block model until, looks like there's maybe one block between the surface topo and the model there. All right, that looks good. As far as the cross sections themselves, you see those here. Let's now try and simulate those. Here's the one I just looked at, that $20 market price. And that's where you saw that pit shell coming down. I mean, it's kind of still poor quality, but the only reason we can get there is because it's so close to the surface. We can't get down to this higher quality down here because we'd have to move all these gray waste blocks to get there, which would cost too much. But once you get above that, even just a $2 difference, I can now start my second pit over here to the left where that higher quality ore is. Now these cross sections, I took them from this blue line, and it's a little misleading on looking at the model and how deep it can go, because if you recall, that model is at an angle, the vein. So if I go back to the viewer, it's not straight up and down. So that's why the cross section is not going to show exactly the bottom of the ore. So if I just tip it right there. So it depends on the map. If my cross section line is here, it's going to be straight down. The model would stop there. If my cross section line is here, I'm not going to show the upper blocks, but I will see these lower blocks. So you really can't do a cross section at an angle, I don't think. You have to check that one out, but that's the reason that it might look a little strange, because I can't capture the entire vein on my cross section. So this is the $22 one, and then 35 gets a little better, and it does a nice job even on multiple pit bottoms. You can see here I've got 2 pit floors with a little saddle in between. And the way these were generated then, we'll go through on that exercise, because it's a cross-section through the block model, superimposing your tin file surface on there. Now, if you recall, those were, and we'll do the $32 one too, which would be somewhere between these two. And we'll measure the high wall angle at the end to make sure it's 65 or whatever. Close to 65. You can see it's not going to be exact because they are blocks. All it can do is analyze blocks, and it just picks out one block at a time. All right, so the way you generate cross sections then would be under Straticalc, fence diagram. It's the geologic cross section routine. Our type will just be on a 2D cross section, which is what these are. Our source will be from the geologic or mining model, which is in fact our block model. If you had multiple lines and you wanted to generate all these at one time, you could do so. Just pre-name them and you can generate many cross sections at one time. But we'll just do the one. Our grid. I'm going to double check the grid here. This is 50 feet, and that's 50 feet, so there's no exaggeration. The vertical scales should match. No problem there. 50 and 50. This is metric, so sometimes in a metric drawing, you should have scales larger than what you think. I'll leave it at this and see how the text appears, but sometimes the text might be too small. This interval, x-axis grid interval, is the stationing there. Set that to 50. And then the vertical would be the stationing going up, also 50 meters. Fix only. All right, that's all good on the grid spacing. Then we go to the draw tab. We're going to hatch the fence, obviously, because that's what you're looking at here are the hatching solids of the blocks. So let's check out the hatch settings first. That's very important to make sure we have hatch by block model turned on. Nothing else of importance there. Just make sure the hatch by block model is on, and it'll ask us for the grades later. So we close the hatch settings. We don't have drill holes or geologic columns to put on there. No pit lines, no faults. But the other one to turn on is here. It's draw additional surfaces. And you can see that's what this red line is. And if we turn that on, we will be prompted for, you can have one or you can pick multiple new surfaces to put on top of your cross section. And that's how I did these red lines here from the pit shells. And that's it. We hit OK. Choose the geologic model. And then the copper grades, which is just the colors for the 1, 2, 3, 4, 5, and the waste. And then here's that new screen we didn't see before. The layer is surface. I don't think it's going to be red. I'll change it when it's done. And then let's pick that other grid, or tin, I should say, we just made today. 32. Revenue, $32. That's dated today. The rest of them are a week ago. And then OK. But notice you can add multiple and draw all sorts of pit designs and benches, other maybe faults onto the cross sections if you want. All right, pick polyline for the fence diagram. So go back to the plan view and just pick that polyline. Starting at a -150, which I think these are, that makes sense. Yeah, it always finds a logical starting and ending elevation. So you can usually just hit enter. Top is 200, elevation, enter. And we'll put the $32 one right up here. I must have had something else turned on. This is, okay, it's a solid. So that would be some bedrock below the block model, but not a big deal. The black up above, that is the material between the top of the block model and the surface topography. And that's why I had to fill that in with something. And then we can just change the color of that line to make it red to stand out. Actually make it yellow, maybe. And I also have line weight turned on. You see, we didn't really discuss line weight, but if you're an AutoCAD novice, there's something that is down below these line weight displays. You can give a line weight, it's a weight, but it doesn't change. So if I zoom in or zoom out, that line stays the same. It doesn't change. Whereas if you had an AutoCAD thickness, maybe of 5 feet, and you zoom in, it'll get thicker and thinner as you zoom. But the line weight is good for just emphasizing polylines. And that's part of the properties of a polyline. You can give it a line weight here in millimeters. You just pick on something, highlight it, change its weight. Maybe I'll make it thicker yet. As I zoom in, it stays the same. It doesn't change. And that can be plotted too. So if you go to File and Plot, there's an option for plotting line weights somewhere. I guess scale line weights there. This is a little different than the AutoCAD plotting window. I know it's there in AutoCAD, but in IntelliCAD, I guess it's right there. It's just allows you to plot the line weight. But that one's a little bit too thick, so I'm going to drop it back down. Or it's a switch, you can just turn it off altogether. So the entire drawing has no line weight active, and they're all just shown there as the smallest increment, which actually is a line weight, a line thickness or weight of 0. Okay, so that's how we would do a cross-section fence diagram through the block model, posting or drawing our designed surface on top, emphasizing it with some line weight. As far as measuring then goes, we had our steepest slope, I think, set to, was it 65 degrees? So let's kind of look at some of these. If you were to do, I don't know, let's just do like a polyline. Go from maybe rough draw it in about that slope, and then come over to the right. So that's about the angle you see there. And then if I were to inquire and do an angle info on what I just drew, pick the two sides, 60 degrees on that one. This one looks a little better. And it just depends how you draw the line too. If you maybe go crest to crest of the blocks or toe to toe. But I'll just sort of do best fit on that. And then over to the west and move that over here. It's about the same. Looks very similar. That was inquiry. Angle info, just pick the two parts of the angle. It's right at 60. All right, well maybe that's what I used for the design. So let's measure today's. I think I might have done 60 then. So this looks a little steeper. This is probably going to be closer to 65. Snap to the end point, bring it over. I'm not even going perfectly orthogonal, but it's close enough. And then one more measurement, inquiry, angle info. There we go, 66 degrees. So that's, the calculation was done, if you recall, from this window right here. And here I'm showing 45 degrees, but that'll be the next project we work on, the stratified one. But that's where today I punched in 65 degrees, but I believe, obviously it appears, when I built these other surfaces, I used 60 degrees. And that's where you set those. And you can change that, again, north, south, east, and west. All right, it's looking good. It's a little bit intimidating, I'll be honest, at first, but once you just get in there and look at the screens, I'll bring them back up, again, when we go back to it. There's really not a whole lot to it. You just need to be clean and careful with your equations. Define your conditions properly, so if you define it if it's ore versus waste. And once you get that defined, then it's quite simple. And it's actually a lot of fun. And here is another graphic showing side-by-side comparisons. Here's the $20 pit and its 3D shell next to it. 22, you can see as the cost goes up, the pit gets deeper and deeper, down to the $65 to there. So I'm curious if we could maybe do like a $90, and if we would actually get down here to the bottom of this yellow and red. I think I'll try that now. I haven't done anything higher than 65, so we'll do that now. And I'm actually going to go, we'll do a 65 angle. That way we can get down there possibly faster than if it's too shallow or too flat of an angle, we might run out of room and go out of our model. But we'll find out. So I'm going to repeat this all, the whole process one more time for review, and then we'll go over to the stratified. Back to prepare value block model. Choose the copper block model. We'll do the geologic stratified model next. And then here are the two that we made today, the two existing value block models. Like I mentioned earlier, you're allowed to reload that, make some changes. You don't have to start way back here on the geologic side of things, but we will, because we're going to make a new market price. Cut the model by the topo. Since I started over, I need to remove the blocks above the topography. Topo grid. Cut above. And switch to equation. We'll select a new equation. And I'm thinking we're just going to load up the $65 one, market price. And I'm going to change that to, we'll go out there and say $90. We should hopefully get way down towards the bottom of our block model. All right, so we've got the 90 there. We're going to do a save as. Save as 90. I haven't done this yet, so this will be the first time. Okay. And it's thinking it's going to give us a economic value here, which hopefully won't be too negative, but it's, I think we had negative 1.3 billion last time. Now we have negative 1 billion. So it did increase quite a bit, actually. The entire model, obviously we're not going to do that entire model. So we hit OK. Save it as market price of 90. It's done. Then you process it with optimize pit design. Choose the 90 value model. And we'll just do the same, azimuth of 0 to 360 at 65 degrees. Give it about a minute or two, and then it will ask us to write out the pit shell tin file. And then we'll draw the cross section and see how we did. We'll look at it in 3D also. And that's where I did these side-by-side comparisons. I just did the fence diagrams, posted them there, and then I went into the block model 3D viewer and just loaded it up each surface one at a time and screen captured it. And then I believe they're individual. Yeah, each one's an individual screen capture. All right, the tin file. We'll drop down here in revenue of 90. Block model to rewrite out is 90 output. And this one finished, let's hit F2. Quite a bit, 297 million and 6.3 million blocks. So cubic units, cubic meters over 50,000 blocks. 50,000 blocks, what was in the document here. This one only had 47,000. So this one did go a lot deeper. And let's see how far down it got. We'll view the block model and bring in the surface. Copper grade file, no waste to display. Kind of neat. You could actually limit the blocks to view by the optimum pitch shell. So that way you don't see any blocks below there if that was an option you need to display. But we'll leave it all on there. There's the model. And let's bring in that new surface we just made for the 90. Didn't do as good as I thought. I thought it would maybe capture these lower ones, but it does look deeper. I was maybe also concerned that we would run out of the model area, but we don't get close at all. We got plenty of space there. So let's just see how that compares to the previous one, which was what, 65. It gets a lot deeper on the right. So that's a pretty big jump in the amount, and we didn't get a whole lot deeper, to be honest. I thought it would go down further. But we did see a huge jump from 20 to 22. Okay, one more thing. Let's draw both 65 on the same, 65 and 90 on the same fence diagram. So we'll go to the fence diagram. It should remember everything we did. I hit OK. Choose the model and the grade parameters. And here we're going to add the 90 and 65 surfaces. So we'll do 65 first. and 90-second. So that way they'll both be shown on the same cross-section. I haven't done that before. On all these other sections, they were all single surfaces, 150 to 200. The hatching of all the blocks. I think in AutoCAD it does that part a little bit faster. All right, so that we'll just change the color on the two. This is the 90 is green, and this is the 65 at magenta. Yeah, I thought it would make a bigger difference, but it's, again, that's a section at that blue polyline. So the blocks do go deeper. Potentially right in here, there's blocks, but it's away from my line. That's why you can't see them, because that vein is going down at an angle. I tried various places to draw this polyline, and I just tried to find the medium point of the vein, but it was difficult. You could probably do 3 sections across there if you find your the pit that you're finalized on. You could do 3 or 4 sections and then see the various sections in 3D. We do allow 3D cross sections. I don't know if that's worth doing here because we have the model, but just so you're aware, under fence diagram, you can do 3D slices of the block model. Tell you what, let's do one. I'll do a north-south one. From there, straight to the north. And we'll do a 3D cross-section through the model. Fence diagram. Fence type will be 3D. I don't think we're allowed, though, to draw additional surfaces on it, obviously, but we could view the block model at least in 3D. Okay. Choose the model and the grades and the polyline. Done. That was pretty quick. So we'll use the orbit. I thought I had an orbit toolbar, but I don't see it. Let's view it from the east. That's it. Nice 3D slice. There you can definitely see the slope of the model going down at that line. These other dots in the background, that's the vein behind or in front of the cross section. But at that blue line, there's the shell. And then I guess maybe in 2D, you would put the pit shell on there to see the north-south cross section as opposed to the east-west cross section. That's a 3D slice, and you can look at it in various 3D angles too. All right, so that's a good place to stop on the copper example. We did 2 more additional ones. We did a $32 and a $90, and got those results written out and had some success there. So I'm going to shut that one down. Close it. Save changes, no. And let's open up the other one, the stratified model. Here we have 3 seam deposit, and they're dipping down about an angle. Let's see, how would you measure an angle like that? Well, you would go to Civil, and under Profiles, it's an odd name. It's called Label Polyline Slope Distance. No exaggeration. Okay, we'll just pick a line, if there is a line. We'll grab this line. About a 30%. Let's go degrees. What's our degree slope? 17 degrees, dipping on these seams down in. So you can see the test here will be to see how deep we can go down and still make some profitable money. And you can see there's some results already showing up, but we'll go through the process now because it is different than the other one, using a geologic grid model versus the existing copper block model. Back to geology and block model, and we'll start over with prepare value block model. This is in a different folder, and so it's looking for obviously the same file types, but we just have the one. It's called optimum pit, but this is .pre, and there you can see the grids. There are no block models at this point, strictly grid files. You got your topo, top and bottom of the 3 seams. Just like that, now we have a different dialog box. We didn't see this before because we had picked a block model, BLK. So as soon as you pick a stratified model, this window appears with all of your beds over here. That's the big difference. And this one does, in this case, it's a bigger area. The blocks are, when it makes the blocks, it converts them to a larger file for the value model. So the concept here is to define what we are after. What are we mining, for example? And how do we want to subdivide it? Because it does have to make a block model to do this optimized pit design. So it's going to look at all these various seams and create individual block models effectively of each one. The ore and the waste. And I've got 6 pages here because I have 6 seams. And I just captured each one to show you the input parameters. So let's just load that and take a look. Well, before I load it, I'll just go through how you fill it in. Obviously, you don't have all as the same. The whole thing is not ore or waste, so you don't want to do all here. Each one has to be defined individually, so we're not going to do anything to the all option. But the first one is overburden. You can see I've got 3 colored seams and 3 gray seams, which is obviously the waste or the overburden to get down to it. And you define it. I usually look at the thickness or the how relative thickness to the other seams and define the block or subdivisions based on that. Or you could do an average thickness of blocks because obviously this gray material varies in thickness, so you just have to put in an average thickness or a min and a max. But in this case, let's hit is or. So you do 2 things here. You tell it how many blocks to divide it up, and you define if it's ore or waste. And this is the same attribute name I just made up and entered in here. Then we can use that same attribute when we write equations. You could just call it here the good and the bad, or whatever you want to call this stuff, and give it a value. Is it 1, 2, 3, 4, etc.? I'm just going with 0 and 1. So the OB has a value of 0. The 475, which is this thick purple, has a value of 1. So that means, yes, it is ore. And the purple, I broke into 5 subdivisions. So let me just load it up and make sure I'm in the right one. Stratified example. It saves it as a PSDB. It's a subdivisions for beds dialog settings file. I'll repeat, like I mentioned earlier, you have grids now. You need to convert that geologic stratified model to blocks to do the optimized pit design. And that's what this first window is doing. And you're telling it, in this case, based on how thick they are or thin they are, how many divisions I'm doing. So the next overburden, I broke out up into 13 blocks. The green seam, I only did 4 subdivisions. This thinner gray, I did 9. It's not ore. And the bottom red, I did 4 blocks, and it is ore. And that's it. So we hit OK. So the block heights then do vary. Because I have the 2, 4, 6 different seams listed here. So once that's done, it takes us right back to the screen, which hopefully looks familiar. This is where we were before. Whereas when you loaded a block model straight away, this window appears right away. But we didn't have that. I will do the cut model by topo one more time, just to be safe. I don't know. We really shouldn't have anything above the topo, but I'll just do it to see. I'll cut above the surface. Yeah, it took away 10,000 blocks above the ground. And just like before, we don't have an attribute already in the model. That's a value. So we'll turn that off and go right back to the equation. This one's bigger. If you recall, yes, or on the previous example, we had 600,000 blocks. This one is 1.7 or almost 1.8 million blocks. And it does take longer to run, so I'm not going to run this one, but we will look at the results. And of course, we got to look at the input now because these equations will be different. And this is different. We didn't have if it's ore or waste at the beginning of the previous example. That was defined later on in the conditions. At this stage, I've got it defined already based on the previous screen. So this one will run a little bit quicker as far as setup goes. All right, so we've got the equation writing window. Again, the equations, conditions, and test. It's all blank right now. Let's go and load up the one we have. And again, I have $3 amounts here, so we'll just pick the middle. Let's see which one. Before we move on, here's just a text graphic of the different seams, how many divisions, and whether it's waste and ore. Subdivision, it has to be greater than 2. You can't have one subdivision, and it's only one block. So you got to have at least 2 subdivisions. And yeah, this is the 50. So I just kind of want to match this one with the same market price example. So there's the 50. It's a DB3 file, database. And this is the name of the file, optimum pit 50, because I have a market price here of 50. And we'll do the same thing here. We're going to talk through these equations. You can just see there's actually fewer equations here than what we had before. I think we had 6 rows before. Now we just have 4 because we didn't have a processing cost isn't part of this. And also we don't have those conditions. Notice there's no blue over here on the right. That was coming from the conditions tab, which we did before. So this one is not in metric. All right, the first thing then I calculate would be tons. So I'm taking the volume of each block, multiplying by a density, which is a constant I've entered in. And the density is 150. That's pounds per cubic foot. That would be for all the blocks. But I guess you could give a density of ore and density of waste if you wanted to. And then just times 27 divided by 2,000 gives us tons. And then I did a similar thing for the mining cost here, which is an equation calculated as these tons times the haul cost, which is 4, just a constant. That's how much it costs just to haul it out. And then I did the same thing for elevation, plus how high we had to bring it up. So that's the cost, maybe like a horizontal cost, and then this is adding to it the elevation lift cost would be the 75 or 7150 would be the height where I get it up to, minus the Z centroid. Again, that's a predefined from the first page. Every block, when it makes a block, it assigns an elevation to its centroid, saves it in the BMV file, and that's one of the attributes then that you definitely can use. So the exit height, or elevation, minus the height it started at, multiplied by the extra cost there, maybe just an extra 1. So adding that much more to the haul cost. If you're at the very top, 7150 minus 7150 times 1 is nothing. So there's no change. You just have a haul cost. But the deeper you go, the more your lift cost goes up, and you're going to increase it. All right, finally, the revenue, what you make when you sell this. We've got the total tons, but we need to remove the waste. And so I'm taking the total tons of the whole project, only the ore, however. So the is ore was a predefined from the first page where I had those 6 seams. So the is or is calculated from 475, 365, and 255. That's the ore that I can sell to the market. The overburden waste I'm not making any money on, but I do have to move it. That's the mining cost. The revenue is just coming from the ore only, times the market price here of just 50. And then the result is, like I said before, always going to show up. You do need a result. That's grayed out. You can't change it. And you just enter in the equation to calculate the result. I think I have the test here also. If not, it's not a big deal. You saw how the test works, but there's just entering in a constant. So here's a hull cost constant of 2.1, but we did the constant entry before too. All right, so I don't have a test here, but the test tab, run test. Hey, that was the right one. I only had 3 to choose from, so that was, if my block, I just chose of an elevation of 6,900 feet, has 100 cubic unit volume, and it is or my result, which is result there. If I did the math on a piece of scratch pad paper, it gave me 9065, and then when I hit the run test, it finds the same result. So that's green. Again, if you change it here, maybe to 51 and run the test, it's going to be red. Say, nope, you calculated wrong, or you're in the wrong equation. Okay, that's it. So we save it. It's thinking. Should give us an economic value here momentarily. I didn't save it though. Okay, there it did. If you mine all the blocks, it's at 148 billion value. That seems high because it's a lot of waste here and not a lot of ore. And then you hit OK, just like before. It creates a BMV file. So we'll just call it the 50 market price. So the rest of this is pretty much just repetition from before. However, I do know from running that in preparation for this that did take 5 to 10 minutes. I can't recall exactly how long, but it was longer than the other one because it is 3 times the size of the block model. So we're not going to do that, but we will look at the results here. We'll look at the model itself, the grids, and then the pit shell. There's a routine. I don't think we looked at it yet. It's StratiCalc down to Geologic Model Viewer. Optimum pit pre. Okay. Yeah, it's dipping around. Wait a minute, it's dipping the wrong way. But there's the grids, and there's no exaggeration. That's really how deep it's going, steep it's going. This is the current surface topography, and so we want to see what let's try bring in the 20, I think it was. Or 25. Optimum pit, $25 tin. Oh, it didn't go very deep. I was looking down here, but it's way up there. Let's turn off the topography. And we'll move down. These are the geologic grids going in. There's the block model it made. That's probably not the best way to view it, but let's turn off the last one too then. Not that one. And we'll color it. See if we can color by elevation. So this is the smallest dollar amount one. And you did see those other grids going way down. Let's turn that one, the bottom one, back on. That's how far down it potentially can go. It's a real thin one, thin seam, so there's not a lot of profit there. However, we are parallel, we're running down to it there, and then we pretty much stop mining that bottom seam. The big, thicker purple one is up here, so that's why we get a lot deeper, a lot better material. That's up here. This is the green seam, and then the purple seam is there. So let's bring in another surface then. Let's grab the highest amount, $75. And we'll turn off the 25. And that's a lot bigger. So this one, you can see we are definitely running down on that bottom seam all the way to there, and then it stops and says, okay, we can't go any further, and then brings it back up, and that was the slope we decided on. It did leave a few little islands in here and also right here. I'm not sure why. I think maybe the seam has a very thin, it pinches out to 0 or nothing, or disappears. This little block here of the green seam obviously wasn't profitable. We got down to the first seam but didn't want to go down to the second or third. Or I'm sorry, this is the first seam up here. That's second, and this is third. So we don't mind this second, the third seam here, just first and second. So we close that, and let's look at the cross sections then. Here we have the smallest amount, the 25. You can see here we do take away the red seam up to there, stop, get the green to there, stop, and then the purple here. This is odd. I think what's going on here is this gets close. So it sees the inner burden here thins enough and says, okay, you can go down and grab that red seam, but only right there. You don't want to take it here because the overburden is much thicker. That's really interesting. But even to do so, you got to move this high wall quite a ways back. But in doing so in that case, then you're getting a little bit more of this upper material. So that's a good example. And then, of course, with the highest dollar amount, it pretty much can take it everywhere, except here's one of those little islands. Maybe that's close to a block where it's pinched out. So I didn't really have any quality in here, but that's another thing you could do is based on whatever the deposit's qualities are. That can affect the market price or how much you're getting for it. And then that can also be used in the equations. But I didn't bring that into the picture because I didn't have any quality analysis. The angle, I believe I used 45 degrees. It looks a little steeper than that, but I just want to measure. Maybe 45. I'm just kind of rough eyeballing in the polyline angle. Move it over off to the side. And that was under inquiry, angle. I bet that is 45. Right on, 44 degrees, what I roughly drew in. So it's a good check on the high wall angles and then the surface. So I do like this aspect of using it on stratified models and existing block models, which is a nice way to visualize going down, especially when the seams are dipping like this. You can see how far down we can go based on the dollar revenue. One more view here of this 3D surface. This is the 50, which is middle of the road, and that's kind of a neat one because it has these little pods here. You can say, for example, you can get right down in there, and the floor is really interesting, I thought. One more time, add the bottom surface, which is the 255 seam floor engineering model. There, that's the bottom.